Hello, welcome to part 3 of the series of finding the domain of a function. And in part 3, I will be dealing with exponential function and logarithmic function. Firstly, let's define what an exponential function is. So generally, you say that a function is exponential if it is defined as f of x equals a to the x. Okay, so the exponent itself is the variable. That's the key to defining an exponential function. The exponent is the variable and the base is a constant. So it's a constant raised to a variable. Look at the contrast. What if it is x to the a? In this case, this is a polynomial, especially if a is a positive integer. Okay, if a is not a positive integer, then it might be a problem because it depends on what that a is. But I'm just letting you see that the constant has to be the base and then you have x being the variable. Okay, so now that that definition is out of the way, we just want to ask ourselves, is it possible that we will plug in a number for x and the answer we'll get, the output of this function will not be real. We'll get an imaginary number. It doesn't matter if this is, so let's look at all the possibilities, okay? It's possible that x is less than 0. It's possible that x is equal to 0 or x is greater than 0, okay? It's also possible that x is a fraction, okay? So these are all the possibilities. So x is negative, x is 0, x is a fraction, or x is greater than 0. Which of these can cause us any trouble? Well, if you check it out, if x is negative, for example, if you say 2 to negative 3, we know we can rewrite this as 1 over 8. Well, this is a real number. So this being negative is okay. There's nothing wrong with it. If we check x is equal to 0, anything raised to 0 is 1, so 1 is a real number, so this also checks. When x is positive, if it's positive, it could be, say 2 to the second, that's 4, or 2 to the 2.5, that's going to be 2 to the 5 over 4. You will get a decimal or an irrational number, but irrational numbers are still real. So remember, the goal of getting the domain is just getting real numbers. Okay, so this also checks. What if x is a fraction? I already did that. Okay, so with this combination, there is nothing. So if you said 2 to the 1/2, or you say, let's use an easier number, 9 to the 1/2 is the same thing as square root of 9, which is going to give you 3. Or an irrational number, remember, it is still real. Irrational numbers are still real. So you can see that there is no value of x that's going to make this function give us imaginary numbers or infinity, unless the input itself is infinity, which doesn't make any sense. Okay, so at this point, the domain of any exponential function is all real numbers. So I'm just going to say here that d is all real numbers. Okay, it is the set of all real numbers, or you can say it this way, that is from negative infinity to infinity. That's it. So this is not a major, let me put this in a box. Okay, so this is not a major thing. Just know that an exponential function where the base is a constant and the exponent is a variable, you're fine. Okay, you're always fine. Okay, however, there's one part that I need you to pay attention to. It may not show up at your level, but you want to pay attention to it. This a cannot be 0, okay, when this is 0. So you cannot have a situation where you have 0 raised to power 0. You know this general rule that anything raised to power 0 is 1? Well, that anything cannot be 0 on its own, because if you have 0 raised to 0, that is indeterminate, and you can't have this. So this is the only thing we have to avoid. Everything else is fine. Okay, let's move on to the next one, logarithmic functions. Okay, so for logarithmic functions, I decided to write 3 key examples I'm going to use just to explain a concept. And once we're done with that, we're done with this video. Okay, so when you take the logarithm of a function, you're actually exercising the inverse operation of an exponential function. Okay, so which means that the domain of an exponential function becomes the range of a logarithmic function, and the range of an exponential function becomes the domain of a logarithmic function. So what that simply means is that if you take the logarithm of x, you expect it to always get real values. Okay. However, remember that a to the x will never give us an imaginary number, so all the answers we get also will be real. Okay. However, the output from a raised to power x, no matter what x is, can never be 0. You cannot raise something to something and get 0. So that means, and remember that you cannot get 0 in the output, which is the range, the part of the range. Therefore, the input for the inverse function can never contain 0. So the most important thing is that you can never get a 0 when you have an argument for logarithm. This x cannot be 0. And even if it's not x, if it is more complicated, like you have here, this entire expression cannot be 0. The base of that logarithm is irrelevant. So do not worry about the base of the logarithm. So let me just write this. So in this case, I'm going to say that f of x is equal to log x. Okay, if I want to write the domain of this, it's going to be, the domain is such that x is not 0. That's one. Secondly, because a to the x cannot suddenly change into a negative. Remember, even if x is negative, it just means, for example, a to negative x is 1 over a to the x. So this cannot change, because the input is negative, does not change the output into a negative. You end up with a fraction. Okay, therefore, you cannot have a negative as the argument. So there are 2 things you cannot have as the argument of a logarithmic function. You can't have a negative value, you can have 0. Therefore, this argument must always be strictly greater than 0. And that's all you need to know. You just want to look for the values of x that will not make it greater than 0 and exclude them. Okay, so let's take all the examples that we have, one after the other. So the domain of this function is such that x is strictly greater than 0. So you're going to say it goes from 0 to positive infinity. That's the domain. Okay, or you can put it this way, that it is such that x is such that 0 is less than x and x is less than infinity. That's another way you can say that. Okay, or you can say is x is a set of x, okay, it is a set of x such that x is strictly greater than 0. That's another way you can say that. Okay, yeah, different ways. Let's take this example, looks like the easiest one. First example, we have logarithm of 2 minus 3x. We're trying to establish what the domain is. F of x equals this. So what would be the domain of this? Remember, we said this must be strictly greater than 0. That's all you need to write. Okay, so you say 2 minus 3x is greater than 0. Not or equal to, because it cannot be 0. Okay, and remember, it cannot be 0 because a to the x can never be 0. Okay, now, so we have to solve this. You have 2 is greater than 3x, and that leaves you with 2/3 is greater than x, or x is less than 2/3. So all values of x less than 2/3 will be good, because we had the best description here from the beginning that what's in here has to be strictly greater than 0. And now we know that this will only happen when x is greater than 2/3. I mean, when x is less than 2/3. So on my number line, this is what I'm going to have. I'm going to have 2/3, and I'm going to look for numbers to this side. So this is going to be an empty 0, and this would be the part that I'm seeking. Okay, and to write that in interval notation, it's going to be that you're going all the way here, negative infinity, you keep going until you almost get to 2/3, and you just stop. And that's the domain of this function. Okay, let's take one that's more complicated. I'm going to get rid of this, and we'll be back. Okay, now we have f of x is log this, and we have that base 3. Remember, we're just concerned about the behavior of the argument, and we said this argument has to be strictly greater than 0. That's all we're asking for. So you need to solve that inequality, saying x squared plus 5x plus 6 is greater than 0. If we factor this, we're going to end up with x plus 2, x plus 3 is greater than 0. Okay? This is what we want to establish, but from here we can find the critical values. Okay, you might just solve it as an equation, just find the critical values, and then you can do the sign test to see whether this is going to be positive or negative. So I'm going to change this, because actually that's the correct thing to do. Just solve this as if it was an equation. So we have x equals -2 and x equals -3. Those are the two values you need to do your test. So for the test, remember that the ultimate goal is to make sure that this is greater than 0. Okay, so let me put it here. X squared plus 5x plus 6 must be greater than 0. That's what you need for this argument to be valid. So now we're going to have -3 and -2. So let's test what regions of the number line will give us values that are greater than 0. You know, greater than 0 means positive. So you're just looking for positive values. So I'm going to take a number in this region. -4 is a good number. Okay. If I plug in -4 into this equation, I'm going to get 16. Or I'm just going to put it here. -4 will make this expression negative. Make this negative. Negative times negative is going to give me positive. Okay. So this region is positive. Okay. So I need this part. Check. Now I go to this part between -3 and -2. That would be -2.5. Okay. If I put -2.5 here, this is negative, and this will be positive. So negative times positive will give me negative. So this region is negative. I don't want this region. Okay. Now if I go to this part, it's going to give me. If I pick a number on the right hand side, I'll take 0. Put 0 here. This would be positive. Put 0 here. This would be positive. Positive times positive gives you a positive. So this region is also positive. So basically what I'm looking for is, can I take these two values? Well, remember that -3 and -2 are those values that make this expression 0, and we can't have 0. So it means we can't have these two values. Okay? So you're going to put 0 here. I mean, an empty circle, and we're going in this direction because this is the positive region. This region is also positive, so we go in this direction, and you can mark it this way. Oh, I love that. Okay, so you can write your answer here. It's everything from the left until you almost get to this point. See, it's empty, so you have to make a curve and write -3, okay? And this is -infinity. Union, what starts here? It starts with a curve also, and this is -2 up to +infinity. This is the domain of this function. Okay, now let's take the last one. This one has a rational argument. Let's see what we're supposed to look for. Okay, so this is the last example I'm going to take. It would be more interesting actually if I change this to maybe something like x. Let me just write it that way, okay? So we just have a more interesting situation to work with. So let me change this. Okay. So now remember that this argument must be greater than 0. Strictly, it cannot be 0. And if you look at this expression, x over x plus 1, this expression can only be 0 if the numerator is 0. This expression can only be be undefined if the denominator is 0. So you want to quickly look for those critical values first, and you can't have them. You can't have them. So you have critical values. One will be for the numerator. Okay, it will be x equals 0. At that point, because if this is 0, 0 divided by this is going to give you 0, and we cannot have 0. So x cannot be equal to 0. So we can say the numerator will give you this. X cannot be 0. Now let's go to the denominator. Now the denominator of any rational expression can never be 0 because it makes the expression undefined. Therefore, x plus 1 cannot be 0. So you can also go and say denominator. So you can say x plus 1 cannot be 0, which means x cannot be -1. So in two ways now, I've told you you cannot have x equals 0, you can have x equals -1, and those are our two critical values that we're going to use for the sign test to see when this entire expression is in itself positive. Remember, it has to be positive and cannot be 0. And thank God that we've been able to identify those two crazy critical numbers. So now let's do this. So here we go. Now, we have two critical values, -1 and 0. -1 and 0. We just want to look for situations that will make this expression to be positive. We just want positive numbers because that's what happens to the argument of a logarithmic function. Remember, this expression is the same thing as log when the base is e, okay? And you just write the same expression as x plus 1. So don't freak out when you see something written this way. It's just natural log. That's the meaning of this, log natural. Okay, so here we go. Now, I have two things to test. I need to test x, and I need to test x plus 1. Okay, we just want to see what the signs will be. I want to show you this other style if you haven't seen my other videos. Okay, so what I want to show you is I'm testing x plus 1, and I mean x over x plus 1. Let's write x here, write x plus 1 here. So what sign will be here? If I pick a number that is less than -1, I pick -2. So it means x is -2. So if x is -2, this is going to be negative. Well, all the x's will be negative. No. Here it will be -2. Here it will be greater than 0. The x will be positive. Now, what will happen here to the sign? If I put -2 plus 1, it's going to be a negative sign. If I take a number between -1 and so -0.5 plus 1 is going to be positive. And then if I pick a positive x like 1, okay, 1 plus 1 is going to be positive. So you see what I have? Negative divided by negative, or a combination of two negatives, is going to be positive. Okay, I need this sign. This is going to be negative, and this is going to be positive. Remember, what we're looking for are the positive areas. So can we have these values? No, we can't have 0 and 1. So I'm going to have two large zeros, and I need the positive region, so I need this region. Okay, I need this region also because it's positive. So just like the other example we did, the domain of this function is from -infinity until you get to -1, not included, union. You go from 0, okay, to positive infinity. Is such that you have that domain. Okay. Look out for the fourth part of this video, because then we're going to talk about composite function, and there's some very crazy functions that I'll be working on because it's a combination of many of these in the same function, and you have to figure out what exactly must be excluded. Don't stop learning. I'll see you when we do composite functions. Those who stop learning have stopped living. Bye-bye.